Hi everyone, welcome back to the Reading Club. This is an ongoing series where I read papers on MIP solvers and then explain them in a simple language. In today's paper, we will continue exploring this paper, which is by Lara Scavuzzo and others, which is Machine Learning Augmented Branch and Bound for Mixed Integer Linear Programming. And in today's video, we will focus on the cut selection part of this paper. So before we start talking about how ML helps with the cut generation, let's talk about how cut generation works, like how cut selection works in a MIP solver, right? So the first point to note is that the root node is a lot more important than other nodes. Okay, so MIP solvers typically spend a lot more effort in adding cuts at the root node than they do for the other nodes. So this paper is mostly focused on adding and selecting cuts for the root node, and the similar techniques can also be applied for the other nodes. So how does the cut selection work in a MIP solver? It's basically they have a bunch of separators. So let's say this is one separator which is responsible for selecting or generating knapsack cuts. So there might be another separator which might be responsible for generating Gomori cuts and so on and so forth. Right? So let's say this is for MIR cuts, and so there are lots of different types of general cuts known to us, and for each of them there is their own separator. So these separators, given the LP solution, they basically generate some cuts and then dump it into this kind of a pool. Let's say all of these are like generated cuts by these different separators. Okay. So obviously before these separators add the cuts to the pool, they do some level of filtering, not the like entire filtering. Some filtering is done over here, let's say. And the rest of the filtering happens by the solver for selecting cuts from this pool, right? So the solver will rank all of these cuts in a particular manner using some criteria. We'll talk about those criteria in this video later. And these cuts are then added to the node. So once these cuts are added to the node, the LP for this node is solved again. And then sometimes we stop, sometimes we just do this entire process again. Like the new LP solution is again passed to all these separators. Separators will generate cuts and then add them to this pool. This pool will now have older cuts and the newer cuts. Sometimes those older cuts are still valid for even the new solution, so they are also considered. Otherwise, they can be discarded. So there are also like limits on how many cuts we can hold in this pool, and when to basically discard cuts from this pool for permanently and so on and so forth. But we'll not talk much about that. We'll talk about how this cut selection works, right? So mostly the focus is on this part. There was one work by Lee and others in 2023. And so they basically focused on selecting the separators, right? So they basically focused on which separator should be on and which separator should be, let's say, off for a given instance. So the details are not much in the paper, and also like the results are not given in the paper, but they say that the results were promising, so we'll buy that. And for the rest of the work, let's now focus on once these cuts are added to the pool, how are these cuts going to be selected? So when we add cuts from the pool to the solver, we don't add one cut at a time. But for now, let's say we want to focus on the single cut selection problem. Okay, so for this problem, what we want to consider is that from this pool that we have for all the cuts, we want to select one cut at a time, just one, and then solve the node LP again, and then repeat this process, right? So solve the node LP, go back to the separators. Separators will add more cuts, and then for all the cuts that are still valid, we will select one more cut, just one cut at a time, and then keep doing this. So the first research was by Paulus and others in 2022. So they used imitation learning. Okay, so what are exactly they imitating? So what is the expert here? So let's first talk about what is the metric for evaluating a single cut, right? So there are multiple metrics, but the metric that they consider was how much the LP relaxation was improved because of this cut, right? So they will measure the current LP relaxation and once they add this cut to this LP, they will solve that LP again, and then they will measure the after cut LP relaxation, and they'll measure the difference between them, and that is the effect of this cut. So their expert is basically evaluating every single cuts in this pool like this, and basically that will select the one that has improved the LP relaxation the most. So that is explicit evaluation. So obviously this is like super expensive. It's kind of like we are solving this LPs multiple times. So basically they will have the LP, they will add one cut to solve it again, they will discard that cut, and then they will add another cut and then solve it again, and so on and so forth. So it is kind of similar to what strong branching is doing for branching. So overall, this process is kind of helpful in solving times if we first of all do not consider the root node processing time into account. In that case, they showed that this way of adding cuts is better than the skip default. But I think we should consider the root node solving time also into account. So there was another work by Tang and others in 2020, and this was reinforcement learning based approach. So again, here the reward is again the same. It's basically like once I have selected my cut, I will add it and I will measure what is the improvement, and that improvement is the reward. So Paulus and others also compared their work to Tang's approach, and they say that this is better for the comparison. But in that paper, they also used the comparison metric, which was kind of favoring this kind of a greedy type of a cut selection rule. So in the reinforcement learning, we are basically not looking at just the immediate reward, but it is also looking at the discounted total reward. So it's not just what happens if I add this cut, but it will focus on how it will change the state, and for once the rest of the cuts are added, overall improvements in the LP objective is taken into account. Whereas the approach by Paulus and others, they'll only focus on the immediate improvement in the LP relaxation. So these are the two works that are mentioned in this paper for single cut selection. So now let's talk about multi-cut selection. So the first approach was by Wang and others in 2023. And this was a RL based approach like the previous one. So their policy would decide two things. So first is how many cuts should be added in each round. So basically like size of the subset that we are going to add to this cut, to this node. And second is that once the size is fixed, then which of these cuts, basically like the scores. So in the cut pool, we want to score each of these cuts and then select this size cut. So it will select that for this round, I want to select, let's say 5 cuts, and then they will score all of these cuts and then select the top 5. And then these cuts are then added to the node, and then this entire process repeats. Now, the interesting part for this work was that the reward was primal dual integral, right? So they didn't just focus on how much the root node LP relaxation was improving, but they said that, okay, let's go all the way to the end and basically solve the entire instance by doing this entire branch and bound process and proving optimality and etc. etc. And at the end, we will measure what was the primal dual integral. And this was the one that they used as a reward for training their policy, which will figure out the size and the scores and everything. So obviously, this is kind of a lot more important metric than the root node relaxation, because ultimately we care about how long it takes to prove optimality to basically solve this instance completely. We don't just care about how much the root node LP relaxation is improving. And these cuts basically have a lot more interaction with the other solver parts, let's say heuristics and pre-solvers. And they are not just used for improving the LP relaxation. So that's the idea behind picking this kind of work. And the downside is that this is super expensive, right? So we have to wait for the entire instance to be solved in order to get our reward. So that basically takes a lot of time. There was another approach by Mark Turner and others, and that was also in 2023. So if I remember correctly, these people are actually the skip developers, and so they basically developed their approach on top of the existing skip rules. Okay, so how does the existing skip cut selection works, and what is their modification? So they basically have four different types of scores for the cut selection. So first is that they measure how parallel a cut is to the objective. The second is what is the integer support. So this basically measures the fraction of non-zeros that are for the integer variables in that cut. The third one is efficacy. So that is the distance between the LP solution and the cutting plane. Obviously, this distance is normalized when we are trying to compare things. And the last one is directed cutoff distance. So this is kind of similar to efficacy in the sense that it also measures the distance between the current LP solution. Let's say this is the LP solution and this is the cutting plane. But they don't measure this distance, which is like the shortest distance. But let's say over here, I have my current incumbent. Then I will measure the distance between this point and the plane in this direction. So this is the distance that is measured. So this is called directed cutoff distance. And obviously when they add these cuts to this solver, to this node, they basically remove all the cuts that are kind of too parallel to the ones that are being added, right? So if I'm adding one cut and this one is, let's say, too parallel to one of these cuts, then it won't be added. So it will be basically thrown back into the pool, and instead of that, something else will be picked. So basically these cuts are kind of orthogonal to each other. Now the problem is that these four different types of scores, how do we weight them, right? So this one can have mu1, mu2, and all these weights. And they said that these weights should basically depend on what instance we are trying to solve. So this weight should not be fixed or static, but they should basically be changed for a given instance. So how do we select this weight? So that's where they introduced reinforcement learning policies. So this RL policy that will be trained on some instances, and then for a given test instance, they will select this weights and use these weights to solve this instance. So in their work, they showed that even this kind of training, this kind of a policy is helpful, and it is actually helping with root node LP relaxation. So when I say helping, they basically also compared it with selecting the cuts completely at random and then selecting these weights completely at random, or basically having a static set of weights. All of these cases, this kind of policy is a lot more helpful. But they also showed that this is not very helpful in terms of reducing the overall solving time. So this is what these people measured, right? So this overall solving time is measured and added as a reward for this work, but not for this work. So overall, this was a very short video. We basically talked about how cut selection works in general and where all machine learning can be used. So we saw some work for single cut selection. And we also saw some works for multi-cut selection. So apart from this two work, there are also some work that basically focus on the configuration. So first one was by Lee and others that we talked about with which separator should be turned on. And so there is also a huge area of selecting parameters that machine learning can help with. So that is, again, of course, a whole another topic. But for these two parts, the prediction is mostly that multi-cut selections are kind of more of an interesting area to watch, because typically solvers don't add one cut at a time, and these policies are never compared directly with these policies. So again, all of this work is kind of a work in progress state. So none of this work is consistently shown to bid the default solver parameters as of now. There is still a lot of potential, and obviously, we can just hope that something good will come out of this works. So this was about how machine learning can be used for cut selection in MIP solvers. So if you like this video, you might want to check out this video where I talked about the same paper and the focus is on machine learning for MIP branching. Last but not the least, don't forget to like and subscribe if you haven't already. I will see you in the next video.